So yeah, I'm Stephan, and I work on the WebAssembly team here in Munich. And I'm focusing on performance optimizations of the JIT engine. And that also means that everything I will be talking about is actually not what I'm working on, right? So I'm just talking about other people's work. But I think it's quite cool, actually. And the reason why I got into using WebAssembly and compiling C++ code is that if you want to do performance optimization, you need benchmarks. So the first thing when I started doing this is I actually started compiling C++ benchmarks. So that's where my knowledge of using emscripten and compiling C++ code to WebAssembly comes from. So I'm not actually working on this compiler. And also this talk is about two things, right? So it says from C++ to WebAssembly, and there's like two things this can mean. One is how do you take C++ to WebAssembly? And that's one thing I will talk about, which is like doing Hello World in different flavors and how you can actually do that yourself and play with this. But then the other thing, which I also find interesting because I like to do compilers, is what does the compiler actually do to take C++ to WebAssembly? So I will also have a little bit of fun explaining to you what's actually happening behind the scenes, just because I think it's fun and interesting to talk about. So to start, we first have to talk a bit about what actually is C++, right? Because there might be people that haven't used it too much. So C++ is a very interesting language because it is one language, but there's really 1,000 flavors of using it. So everybody who writes C++ will write a very different kind of C++. There's modern C++ with smart pointers. There's like C-style C++. If you write a VM, you probably write more like bare metal C++. Right? So there's not really the one thing C++. And essentially, if you write C++ code, you can do whatever you want because you're really close to the machine. Right? Everything is at your control. You have unrestricted access to, for instance, the stack. Right? So if you do function calls, you can look at the stack. You can look at what your callee was. You can manipulate these things, which also creates all the security nightmares we're aware of. Right? Because if you can do everything, malicious code can also do whatever it wants. You can have arbitrary control flow. Right? In C++, you can just jump anywhere. You can have a goto to some label, but you can just also cook up an address and jump there. Right? So in C++, you can go wherever you want. Then we heard this earlier that WebAssembly does sandboxing. Right? In C++, you don't have this. Right? Code is data, and data is code. So you can just write some number somewhere in memory, and then you can jump there and execute it. There's no real difference. Whether it's code or data really depends on how you look at it. And lastly, you have full access to your operating system. So you can call into your operating system. You can do syscalls. You can do whatever you want. There's no like sandboxing. So this is like C++ world to you. You can do whatever you want. It's super powerful, however you like to do it. But there's all kinds of issues when you want to do this in a secure context. So what is WebAssembly? So WebAssembly really is this restricted bytecode. Right? So it's called WebAssembly, but it's not really like an assembly language like IA or ARM. Instead, it is a stack-based abstract machine that executes your code. There isn't really a hardware that can run WebAssembly. And it's also not register-based like most hardware would be. Instead, it has like a stack-based discipline. So we will see how that works a little bit later. You don't actually have access to your stack. Right? So if you do function calls, you cannot actually find out who called you, which arguments are on the stack. There's no way of traversing this. This is all hidden from your code. And that's a great security feature. You only have structured control flow. Right? So you have loops, you have if statements, and you have a switch. But that's it. You cannot just jump anywhere inside of your function. And this will become interesting because that, of course, makes it difficult to compile C++ where you can do this. Code and data are strictly separate. So if you have something that's data, like you're writing some information into memory, you can't actually execute this because it's just data. And on the other hand, code, which is functions you can execute, you can't look at because they are only code. It's strictly separated. And that, of course, also makes compiling C++ interesting. Yeah?
So you can't compile the code, or you can compile it and it doesn't work, and you want to compile to WebAssembly?
So your WebAssembly program itself, it could compile code and put it into its memory, but it could not jump there or execute it. It would just be data. It's separate. And then the embedder essentially provides your operating system. So the embedder provides all the functionality that you require. And of course, if your embedder actually allows you to turn data into code, you could do this kind of thing. But within WebAssembly, you just can't. So how do you then go from this one language completely unrestricted. You can do whatever you want to this restricted bytecode, which is WebAssembly. And we've heard about this earlier. There's this amazing tool called emscripten, right? Which is your compiler that takes C++ or C languages and compiles them to WebAssembly. And this has a long heritage. It comes from ASM.js. It has gone through multiple iterations. But essentially, it's still the tool that you would use if you want to compile your C++ code base. And I won't talk too much about how you get emscripten. You just go to the website and download it there. Google will tell you what it is. But I want to talk a bit about how you actually use emscripten. Right? So how do you now compile something to WebAssembly? So for those of you that are not C++ developers, I've written the canonical example program, which is Hello World. You asked about this earlier, right? Can you do Hello World? So this is Hello World.
One of the possibilities, right?
One of the possibilities. So people that like C++ will tell you, this is not C++. This is C.
Yes.
Of course. So in C++, this is how you write Hello World. Right? So
that's +1 for don't use an end. It's not C++.
I will keep pressing this button now 1,000 times. No, I won't. I only have 2 versions. But this is just to get across the point, right? This is the other way. You have this nice operator here, which you can overload. Lots of complexity. But in essence, this just prints Hello World. Right? So now you have this C++ code. How would you normally execute this? So if you're a native developer, you know, probably everybody knows. But in essence, what you need is your C++ compiler. So I have this simulated bash here, because live demos are hard to record. So you do C++ with your hello.cc file that will spin up your compiler and create these 2 files. First, you get this, it's actually 1 file. You get this a.out. That's your executable. There are historic reasons why it's called a.out, but that's how it is. So you have this a.out, and then you can just natively execute this, and it will say, Hello World, right? So far, so good. So that's not very surprising. So what do we need to do to take this to the web now, right? How do we actually execute this using WebAssembly? So the first thing is you download emscripten, you install it and everything. And then you get this little command, which essentially sets up your emscripten SDK. That's what emSDK means, environment, right? And you source that into your bash shell and will produce lots of interesting output. In essence, it gives you the emscripten plus C++ compiler into your path. That's what it mostly does. And once we have this, we just compile. Right? The big change is, instead of doing C++, it's now EM++. But there's 2 more things I've added here. So I'm saying O3, which tells it to optimize the code. And that's not so much because I want it to be fast, it's because the examples just look better if it's optimized, because there will be less crud. And the other thing is this G3, and that's actually important. And that tells emscripten that I want to have a debug build that contains symbols. Because names in WebAssembly are optional. If you don't pass this, functions will just be numbered. And it's really hard to look at your code and think, okay, function 42, what was that now? Right, so that's what G3 does. It keeps names, in essence. So what has this done? So you get a couple of files. You get aout.js. And that's your JavaScript shell around your WebAssembly module that essentially contains the parts of the operating system that normally would be in your libc, and a little bit of helper script that allows you to just load this up in a JavaScript engine. And it will actually load this WASM file, and that's your WebAssembly module. So that's where actually code is contained. And then there's a 3rd file, which is called a.out.west, and that's a text representation of your WebAssembly. And that's also a side effect of using G3. It will not only compile it, it will also print a text representation of the WebAssembly for you to inspect. What I find interesting here, so this is so compatible to C++ that all the stuff is actually still called a.out. Right? That's pretty neat. So what does this WebAssembly text format actually look like? So here's the example. It's actually a lot longer because it contains a lot of code. Right? Printing to standard out in C++ requires a lot of machinery around streams and everything. But this is main, right? And this is how you read this. So in essence, it says it's a function called main. C++ likes underscores. This gives the type of the function because WebAssembly is typed. It's a typed assembly language. Type 19 means you have to look in a table, and there will tell you this is a void function. And that returns an int. And this is the actual code it will execute. Right, so this is a stack-based machine. It first pushes 3 integers onto the stack. and then calls this function, which has a really long name due to C++, but in essence, this is the write to stream operator in C++. So now you might wonder, where's my string? Okay, so 3 integers. So these two are essentially indices into your memory. This is the index in the memory where your data structure for the stream lives. This is the index into the memory where your actual string lives. And this is the length of the string. So we pass all these strings to this function, which will do the printing for us. Yeah?
Why do we have an I32 but a type 19 for void?
Because this comes from a table, right? For efficiency, function types are in a table so that you don't list them again and again. Right? So you have one table that lists all function types that appear in your module, and then you can just reference them again. Right? So this is the call, and the stream operator in C++ returns the stream again, so that you can kind of have multiple calls. But this is a stack machine, so we don't need the stream, so we have to explicitly drop it from our stack, and then we push the result, which is null. Right? So our function returns null. So this is hello world in WebAssembly. Right? This is what a WebAssembly actually looks like. And as you can see, it's actually quite compact. It's not a real assembly language, but it's quite efficient to compile if you want to take this to native code. And that's coming back to the question, that's why you can compile something so quickly, where the C++ compiler takes a long, long time. This is way, way lower. Coming back to my shell, right? So we have this JS file. How do we actually execute this? And that's quite simple. You just pass it into your JavaScript interpreter of choice, right? So I've used V8 here, which is the JavaScript shell for V8. And you just pass the file, and ta-da, it says hello world. But the cool thing is, this is WebAssembly. You can do the same thing with Firefox, right? So Firefox's shell is called JS. You pass in your AOut file, and it prints hello world. So that's hello world in WebAssembly. Now the thing is called WebAssembly, right? And you're seeing a shell here. And we had these questions before. How does this work in the browser, right? How can I actually print to a string in a browser? The way to do this is actually quite simple if you know. You call emscripten again, but this time you tell it what the output file should be called. And I call it hello with a suffix of HTML. And this tells emscripten that you actually want to create an HTML file. So I will produce one more file for you, which is hello HTML. And you get a JavaScript file, you get a WebAssembly module, and you get a WebAssembly text representation. Now you can't open this directly in a web browser for security model reasons. So you need a little server, and emscripten gives that to you as well. It's called emrun. So you call emrun with no browser and a dot that says, I don't want to open a browser, I already have one, and dot is my document root. And it will then tell you where this is now accessible. So it just spins up a little web browser, a web server for you. And then you can actually open it in a web browser. And now this doesn't look like your normal web app, but in essence, it creates this virtual terminal here for you, which you can print to. And again, right, it says, hello world. Yeah.
What are the security reasons that forbid running Wasm directly?
The problem is so the JavaScript has to load the WebAssembly module, right? So you have to load something. And there's some cross-site origin policy. I'm not a web developer. Web developers in the room, you probably know this better, right? But it's your loading, you have to load another file. It's not self-contained.
Okay, yeah, can't load it from disk.
Yes.
But you could embed it as a string.
You can. So emscripten also has a mode where you embed it as a string, but that's not very efficient size-wise, right? Because then... More questions? Yeah.
Well, your C++ program had implementation undefined behavior or defined behavior because it did not have a return. Is the WebAssembly specification also includes implementation defined behavior or undefined behavior? Or everything is assured to run in the same way in all the browsers?
Yes. So the undefined behavior ends after your C++ compiler. Right? So the C++ compiler can compile it to WebAssembly in some undefined way, because C++ semantics don't say what actually has to happen. But the WebAssembly that comes out will execute the same way in all browsers. right?
But then it's still in the browser. It will still be translated. So the engine in several
But that
browsers will do the same thing.
But that's deterministic. So WebAssembly is fully specified. So the
Guaranteed.
code will execute the same way. You just don't know what your C++ compiler will do, right? Because it can do
That's
what it wants, in essence. So you still have undefined behavior in that sense, but it's portable undefined behavior in the browser.
And the Google specific question, Google has been trying to push HTTPS for everything. Will WebAssembly run without HTTPS?
It doesn't make any difference at that level.
Okay, so it doesn't care about it.
So, how is HTTP involved at all in this? Not at all, right?
Well, you load so your web page loads the JavaScript, and then it has to load this WebAssembly module somehow, right? Or you embed it, or yeah.
What is the reason that we need this JavaScript module? Why can't we load the WebAssembly directly?
Or you can write, so the code inside of this JavaScript module you can write yourself. Essentially, it loads, it does a request for the WebAssembly binary, it creates a module, instantiates the module, and then it contains the glue code to actually do hello world, right? So it implements the part of the operating system like put char and these things.
Okay, but this could in the future go away, right?
Or you can write it yourself, right? So this code is from emscripten. If you use a different compiler like the Go compiler, that produces different code again.
But, I mean, it's not the plan that like WebAssembly has a strict dependency on JavaScript, right?
No, but in the browser it has, because browsers execute JavaScript, and then you have to jump from there. That's the current model. But if you embed the WebAssembly engine somewhere else, it's up to you. So there's no tie between that. Just for in this implementation where it runs inside a browser, that's how this works. So I talked a bit about how you can build WebAssembly out of C++. The other question is what actually happens behind the scenes. Right? So what does the C++ compiler do to actually create WebAssembly? And that's just now for fun, so it's a bit of a shift. As I mentioned before, there's this thing of unstructured control flow, which is allowed in C++, which essentially means you have gotos, but you can't have that in WebAssembly. It just doesn't exist. So to give you an example, I created the unstructured control flow version of Hello World. So this also prints Hello World, just in a very contrived way, because it wants to use gotos, right? So this starts at the top here and prints HE, then goes to label 2, which will print the L, and then as the state is still 0, it will go back, print another L. Now the state is actually 1, here the state is 2, so it will go through label 3 and print the O. Now the state is still 3, so we go to label 4, print the W, go back to label 3 to print another O. Now the state is not longer 3, so we go to label 5 to print the R, then go back to label 2 to print another L, and then go to label 6 to print the D. It's a very contrived example. I give that to you, but this is valid in C++, right? Because you can just do whatever you want. You cannot compile this to WebAssembly because there is no goto. So what do? A very common trick is the switch inside a loop transformation. And that's, for instance, what the Go compiler does. So the Go to WebAssembly compiler. And the idea is, as I cannot jump to labels, I just make them cases of a switch. And then I encode the address I want to jump to into a local variable. So what does this look like? So this is the switch inside of a while loop edition of Hello World. So let's try this. So we start with target, and initially it's 1, you have to believe me. So we go in here in case 1, we print HE, then we set target to 2, and break. So we spin around in the loop once, come back to the switch. Now it's case 2, so we print the L, we go to this if statement, state is still 0, so we set target to 2, we break, we spin around once in the loop, we go back to case 2, right? You get the idea. And this is one way of doing it. It's a very simple way of doing it, but it has the disadvantage that it creates code that's a bit complicated to understand for even a compiler. So the resulting control flow doesn't really look all that nice. So,
are you sure that this is not the way you should write understanding?
for human consumption, this is a nightmare in any case. Yes, but even for compilers, this is not optimal. So when they did the original emscripten for asm.js, they came up with this algorithm, which is called RealUper. And I found this so interesting that I just wanted to talk about it. So that's why we do this here. So the idea about RealUper is that you take this code and try to produce loops out of it again. But you don't look at the source code, you actually look at it like a compiler. So how does a compiler see the code? So I draw this for you. So this is the compiler view of the Hello World example. And in fancy names, so this essentially is your basic block, and this edge is a transition. Right? So you start your program here, then you go to HE, then you go to L can go to itself, it can also go to O, which will go to W, which will go back to O, which can go to R, which will go back to L, which will go to D. So this is how a compiler sees your code. So how do we from here reconstruct loops? And this is just for fun. So I actually will show you the code. This is the loop nesting that you will get. And this is JavaScript for a change, because I thought I catered to both audiences. All right, so I have this print here, and I have these loops. But the interesting thing is, I have a label in front of the loop. And that's something that JavaScript has, and also WebAssembly. You can actually break, continue to labels. So this will continue at that loop, right? That's what that does. So how did I come up with this magic piece of code? Well, I just followed the RealUper algorithm. And the idea in that algorithm is essentially, there's two kinds of blocks. There's the blocks with a single entry, that's just one arrow pointing, and they are pink. And then there are the blocks with multiple entries. There's multiple places that go to these blocks. So those are the blocks we actually have to jump to, right? And they are blue here. And now you create code. So whenever you start with a beginning, and whenever you see a purple block, you just put the code there. You don't need to jump there, so you can just put it there. So we have the HE. Next, we have this L block. And L is blue because there's a lot of edges that go into L. So we need some way to actually go back to L. So we put it into a loop. Right? We put a while loop here and give it a label. So from this L, we can then go back to L. That's this first statement here. It goes back to itself. But we can also go to O, which is another blue block here. So it's blue, there's multiple entries. We need to be able to jump to it. We make it into a loop. So we have loop 2, which prints the O. And then the L can also go to the D. But D is purple, so we can just put the code here. You don't need to jump to it. Next we look at O. O can go to W. So W is a purple block. So we can just put the code here, but we then jump back to the O block using this continue. And that's how we do our go-to. We just continue this loop. And O can also go to R, which is here. And it's a purple block, so we just put the code. But R will actually go back to L. Conveniently, L is a loop. So we can go and continue to loop 1. Right? And this is RealUper.
Are there cases which are not transformable?
That's a good question.
Because this is a deterministic state machine, right? If it's not deterministic, if it depends on the environment of the states in the system.
How would you build such a single-threaded program that's not deterministic?
Okay.
Go-tos always use labels.
So the question here is not, so you're actually saying you don't know which of these edges you will take, right? But that just manifests in these conditionals here, right? So this deep non-determinism. The question I don't know is whether any kind of graph you can draw with edges here can actually be transformed. I don't know.
I think so.
Andreas says yes.
Okay. I mean, you actually have to prove that, right?
So there's a paper for that.
Okay.
Is there a proof paper?
I think so, yes.
Okay. Cool. So yeah, maybe there's a paper. Yeah.
I think maybe to give a bit of context what this is about. So this is basically talking about how you make native code secure, because you cannot jump to places
Yes.
where you could just create security issues. A lot of applications always have security issues because you can jump out of an array, for example. And this is a way to prevent that at a very low level.
Yes. So that's the reason why the WebAssembly engine can only do structured control flow, because you cannot just arbitrarily jump around, and you also, as code and data is separated, you cannot just jump across boundaries. But I think, yes?
Can you like quantify the performance overhead of this, like security?
So the good thing is, once you have like this RealUpified thing, if you put this into a compiler, what comes out is essentially exactly this. Right, that's the idea. So for the compiler, it really doesn't make a difference. So as soon as we read in the WebAssembly bytecode, it just turns into these blocks with transitions again, and then it's fair game as before. Yeah.
So essentially, compared to the switch solution, we got rid of doing extra cases for blocks that are not entered from many different developers. Right?
In essence, it also happens that compilers just understand this better. Right? It's easier to, they will recover that better.
Isn't this, I mean, last time on the last meetup we heard that there are some problems with exceptions, right? So wouldn't this be a method to transform exception-based code into something which is structured, which is a structured control flow?
It wouldn't be zero cost exceptions.
Well, I'm just...
well, the problem with exceptions is less...
because this is also an unstructured control flow, right? Exceptions are also unstructured. If you can convert that kind of, go-to code into something which is a structured control flow, you should be able to convert exception.
But you're thinking within a function body, right?
Yeah, it has to
right.
jump.
So this is only within a function. Exceptions can also be able to leave
Okay.
functions and be caught somewhere.
So this...
So this is a very local thing. So also C++ wise, it doesn't really help if you jump somewhere arbitrary, right? That
well,
you can't.
unless you want to.
You can, but that will be hard to compile. Right? So we're a bit late, but I have one more if you're interested.
And by the way, how does it translate exceptions in C++? It's like every function is no except?
Oh, it uses the JavaScript exceptions at the moment.
And to expand, by default, it just ignores them. But there's a mode where you can actually enable exceptions at different granularities. Just knowing there was an exception, knowing what kind of exception it was, right? Because there's a cost to this. Right? So emscripten has multiple options. How you want to translate exceptions.
To the thing we saw earlier, the slide one before. When does this happen? Does this happen after the native compiler ran?
emscripten does this for you.
But when? In which pass?
In which pass inside of emscripten, or
Like after the like for example LLVMIR is generated or before, like, because this looks like with constant fault we could get back to our initial hello world.
as I said, I don't build the two chains. I don't know where exactly this runs.
That's actually the question. I mean, does it transform the C++ code, or does it transform some sort of
No,
intermediate
this happens on this intermediate, and it also doesn't create JavaScript, right? It creates WebAssembly.
something? Yeah.
Right?
But like, is this optimized again?
As it went.
I mean, like, because I'm pretty sure if you,
When jitting, right? Or during
yeah,
the...
but like this could be optimized like unrolled again because there's constants in there, so we could constant fold them and then.
I can write on it. I don't know whether the WebAssembly bytecode is optimized and at what stage this runs.
But it's reproducible, right? Everybody can go and try it out.
Yes, you can just go and try it.
Because that would be very interesting. See what
But emscripten will output WebAssembly and not JavaScript. So you
Anyway,
will see WebAssembly bytecode. So I could do one more or wrap up, depends on how your energy level is.
One more.
just go on.
So the other thing is function pointers. So one thing I said before, like C++, data code, it's all a bit of the same. WebAssembly is strict separation. Right? And then the question is, how do you actually compile function pointers, which is like a piece of data that points to code, into a language that cannot really represent this? So here's another hello world. This is hello world function pointer edition. So you have a function called hello, which conveniently prints hello, and you have a function world, which does the same with world. And then you have a main function, which in essence defines this local variable called printer, which is a function pointer. And then inside of this loop, it first assigns hello to printer, goes out of the switch, calls that, so we'll call hello, and goes back in here, assigns world to this variable, calls world, goes back one round, and returns. Right? So this is a very contrived way of writing this, but what this essentially does is it assigns some code to a variable, turning it into data that can flow around in your program. So how would you compile this in WebAssembly, where code cannot be data? And the way around this, because of course when it was designed, this is a use case you have to think about, is there's tables. So one thing you can do, you can put functions into tables. And that can be WebAssembly functions, can be JavaScript functions, any kind of functions. And then you can call these functions in those tables via their index. So that means whenever you turn a piece of code into data, like taking the address of it, this will put this function into a table and actually return the index into that table. So this would get an index, this would get a different index. And then when you do the call down here, you're actually following a function pointer, but you're looking up the function at an index position in a table. And tables only contain code. So you keep the separation between code and data, but you have a way to actually pass them around as values. And you can look at this like WebAssembly style. So this is the code that will be generated, a piece of it. So this is your switch. Right? You remember we had the switch where you assign two values to this printer variable. This is your printer variable called $1, and you set it to this value, 330. And that's essentially your index into your function table. Or in the other switch case, you set it to 331, which is the other index. And then when you want to call a function, you have this call indirect, and that essentially loads the index, does some more offset computations to compute the final index, and then calls the method there. So that still keeps data and code separate. Another thing that's interesting here, it says type yada yada up there. So this indirect call is a typed call. So you're calling whatever you find in this table, but only if it adheres to the signature here, in this case being a void function. And that again is different from C++. So if you do things in C++ like taking a pointer, casting it to some random other type, and then calling that function with the wrong signature, that will not actually run. Because there is type checking at runtime whether the function you call from the table actually has the expected signature. And that's again for security reasons.
Is it guaranteed you always know all possible functions and can put them in the table?
No.
So some combinations will fail on
There's things in C++ you can write that you cannot put into this.
So will it fail at compile time or at runtime? If you compile a code which tries to invoke something as a function which is not a function.
So I think that, again, I don't do the compilers, but that depends on the situation. So there's patterns that just cannot be compiled, and that will fail at compile time. But there's certain type mismatches that the C++ compiler will not catch, and that will then probably fail at runtime. But what happens when? I don't know. Yeah.
About separation of code and data, you can still generate code and then ask JavaScript to execute it.
So if you leave the WebAssembly context and go to your embedder like JavaScript, right, that can still do whatever it wants to do. So you could in WebAssembly create JavaScript code and then ask the JavaScript engine to eval it. Or you could create WebAssembly bytecode and then ask the JavaScript engine to actually instantiate it. But it's always the embedder that has to actually do this for you. The WebAssembly module itself can't do this. Okay, and with that, I think I've taken enough of your time. So I will hand it over to Andreas, who will... Oh, unless you have more questions. Sorry. Yes.
So in C++, we can write some CPU-based code, like if-then conditions. Like if Windows 64-bit CPU, write this code, like compile this code. So in that case, what does this WebAssembly compiler do?
You can't write this.
Yeah.
Right. So because you're compiling to this virtual WebAssembly machine, to this abstract machine, and that's your target.
So we have to
So it's actually
choose
not
one
the
of them.
compiler, it's the pre-compiler. I mean,
Yes.
it's
Yeah.
preprocessor and
And that would have a new flag like WebAssembly. Instead of IA, ARM, you would have
I see.
WebAssembly, if that's needed, or maybe the IA version will work. I don't know. But you cannot gate statically on where you're running it. But yeah, I think I have to take more questions offline because otherwise Andreas has no time to talk whatsoever, and that would be unfair.
Let's
So,
have a 5-minute break maybe, so everyone can refresh himself.